All right, this is a solution to number 20 from particle kinetics. Um, it looks like this. Uh, there's a ledge with a pulley at the corner, and there's a box here with a mass of 5 kilograms. And a cable that connects that box to a 3 kilogram hanging mass. The coefficient of static friction between the 5 kilogram box and the ground, U sub S, is 0.5. And it says the boxes are at rest, and it asks whether this 3 kilogram box is going to make the 5 kilogram box start sliding. Okay, so what we're going to do is we're going to figure out what the maximum static friction could be. And we're going to then calculate what the friction would have to be to keep these at rest. And we're going to compare those two. If the required static friction to keep them at rest is less than the maximum friction that could occur with that coefficient and that normal force, then they're going to stay at rest. So that's the idea. The good news about a problem like this, where we're going to calculate when they stay at rest, it takes out some of the complexities that come up with figuring out accelerations. We're not going to have to relate the acceleration of one to the other. Okay, let's go through it. So like always with problems like this, we're going to start with free body diagrams of the two bodies. And it doesn't matter which one you do first, but I'm going to start with the 3 because in this case, it turns out we're going to be able to solve something just from the 3 by itself. So the 3 kilogram mass has a weight force of 3 times 9.81. And a pulling force from the cable. Put that into Newton's second law, and you get 0t plus 0, negative 29.43 is equal to the mass times the acceleration. These are at rest, so the accelerations are 0. And so what you get from this, the y equation says t minus 29.43 is equal to 0, or t is equal to 29.43. Okay, so that's good. So because when we do the free body diagram of the 5 kilogram box, we're going to have a t in there, and now we know the value for it. Okay, so free body diagram of the 5 kilogram box. We have a weight force. That's 49.05. We have a normal force. We have the friction force keeping it from moving. If there was no friction, the 5 kilogram box would accelerate to the left, so we know this friction force is going to the right. That's the thought process for static friction. Remember, that's different from the thought process for kinetic friction if we were talking about this already sliding. In that case, it would just be opposite the velocity vector. But for static friction, the direction of the friction force is opposite the acceleration that would occur with no friction. Okay, and the magnitude, we don't know. We're just going to calculate what that has to be. And the only thing that I'm missing still is the cable tension. That's a pulling force this way, and we figured out from part, that from isolating the other one that this is going to be 29.43. All right, Newton's second law says negative 29.430 plus 0, negative 49.05 plus 0n plus FF0, that's the force of friction, is equal to the mass of the object times its acceleration. And again, we're assuming everything's at rest, so this is zeros. Okay, so what do we get? We have two equations. The x equation tells us that the force of friction required to keep this at rest is 29.43. The y equation tells us that the normal force is equal to 49.05. Okay, so now does it move or not? We know that if it's not going to move, the friction has to apply a force of 29.43. So now we just have to compare that to the maximum. The force of friction maximum is the coefficient of friction of static friction times the normal force. Which is 24.525. And that is less than 29.43. So in other words, this amount of friction cannot provide enough force to keep these at rest. And so the box will move. Okay, so that's how to deal with kind of static friction problems in general, and specifically number 20 in particle kinetics.